we are live across the platforms, YouTube and LinkedIn. Welcome everybody to our first live event on this new series dedicated to open source. So the idea is we'll invite companies and individual developers building new open source tools so they can share with the community. So it's really great to have Ahmed Darwish here with us from Qoro to talk about their new open source project, Divi. So Ahmed, without further ado, I will hand over to you. Maybe you can introduce yourself and Qoro, and then you can take over. So thank you so much again for joining.
Yeah, thank you, Bambodi. So, hello everyone, welcome to the stream. I'm Ahmed Darwish. As Bambodi mentioned, I work for Qoro. I guess maybe I should already share the slides since there are also some more introductory information there. So let's do it and take it from there. So here we go, and then so full screen. All right, here we go. So yeah, as I was saying, I work for Qoro Quantum, and basically, if you hadn't heard of us before, what we are trying to build is the missing link in the middleware layer of quantum of the quantum software landscape. And today I will be talking about Divi. Divi is our open source SDK that helps you interface with our execution layer and helps you scale up your research and your experiments very easily and very seamlessly. So what we will be covering today is I will be introducing Divi through a very simple example and then describe the mental model that you should keep in mind when running Divi programs, as well as implementing your own custom workflows in Divi. After that, I will be walking you through a live demo, a web application that helps you see the different knobs that basically have access to different features that you have access to when you're setting up or declaring the configuration of your Divi setup. And after that, I'll quickly mention some other features that are kind of unique to Divi. So these are some ideas that we have adopted from other open source quantum programs, but have adapted to our much more seamless, even more efficient abstraction of quantum execution. So before I get into Divi, I would like to give you a bit of a preview of our entire stack. So as I mentioned before, Divi is the Python SDK. So it sits basically right at your face. This is what you interact with mainly when you're trying to build quantum workflows using our stack. And once you have declared and set up the configuration of your quantum execution, your quantum configuration, you can then run it locally or through a cloud platform. And for this, we have Maestro. So Maestro is our C++ simulation engine that gives you access to different simulation techniques. So state vector is one of them. It's like very common in many quantum packages. MPS, matrix product states, matrix product state as well, and others which are not listed here, but you also have access to things like path integral or Pauli propagation. And all this can either run on CPU or GPU, but also in basically different kind of machines. So either locally on your very simple laptop, all the way to an entire HPC cluster. And as I mentioned before, we have a hosted platform where you can easily point your quantum program to. So once you have smoke tested, once you have quickly prototyped a quantum algorithm, a quantum experiment locally, you can then easily switch to the cloud platform and scale it up to much more interesting problems. And so this is how a very basic VQE experiment would look like in Divi. If you are familiar with Qiskit, this would also look very familiar. So you have this higher level class, which takes as input the problem. So in this case, the problem is finding the ground state energy of a hydrogen molecule. And in this case, we are interfacing with pinylene, given its very nice and intuitive quantum chemistry module. And once you pass in the molecule, you then can declare the standard configuration of a variational quantum algorithm. So in this case, you have the ansatz, the number of layers of the ansatz, and then the backend, which in this case would be using the master simulator locally, and then the optimizer and a seed for reproducibility. In this case, it would be determining the sampling random state, but I mean, you don't need to care about that. And once you declare the class, you simply call run on that class. This would start the quantum execution process. And finally, once that's done, you can then just call, basically inspect the energy through this best loss property. And so if I would kind of summarize this in kind of like 3 clear steps, I would do it in this form. So you first declare, which we have done here, you run, and then finally you get access to the result. And take note of this kind of run verb, because this is how it's gonna, this is like a persistent verb that you will be able to see in any executable kind of like abstraction in Divi. And as you can see here, like this same pattern scales to larger workflows. And we will get to that in a minute. And so going off on a little tangent, someone might be already wondering, why do we need another toolkit? And the goal here with building Divi is not really to have yet another quantum framework, because we have many of those. We have pinylene, we have Qiskit, we have Circ. We also have, I forgot the name of that other one, the one from Japan. But I mean, that's not a problem. What Divi is trying to build, or kind of streamline, is not the process of building your circuits, but rather streamline the process of batch generating those circuits and easy orchestration of higher order quantum programs. So quickly going through comparison between Divi and pinylene and Qiskit here. So low-level circuit control or circuit construction, you have that in pinylene and Qiskit. In Divi, we don't have our own native circuit objects. We basically interface with pinylene and Qiskit, as well as CHASM. So if you have your circuit objects in any of these representations, you can easily pass them to Divi through an adapter. A feature like a built-in VQE or QA class in pinylene doesn't have that. You need to assemble it yourself. In Qiskit, you have access to them through the Qiskit algorithms module. In Divi, you have them natively. Workflow abstraction in pinylene, you basically interact with your program abstraction through this QNode class. In Qiskit, you generally define an algorithm and then pass this primitive PUB, which is basically a parameterized object plus your set of parameters that you want to run your parameterized circuit in. In Divi, we have this concept of programs and ensembles. And as I mentioned, I will get into more depth on what this exactly means in a bit. And finally, and this is where Divi really shines, is cross-program orchestration, or another way to think of it as like a higher order programs, quantum programs. And in both pinylene and Qiskit, this is user managed. You have to implement them yourself. You have to take care of the plumbing yourself. But in Divi, we have all that built in and can be easily interacted with. So think sweeps of different configurations of a molecule, or think of partitioning a graph or a tuple to a smaller, much more smaller, manageable instances that can be run on a quantum processor, as well as trajectories. And you will be able to connect the dots in a bit. And so Divi already does a bit of like refining of rough edges for very common quantum routines, but also introduces this kind of streamlining of the cross-program orchestration step. And so how is Divi designed? This is the first way of kind of building up on how Divi is able to make the process of writing your experiments easier. So Divi has basically 3 layers, or all of which kind of work through this run verb. And basically those kind of layers build on top of each other. So what we have seen in the example before, that is a quantum program. And this is kind of a self-contained program that kind of solves one problem instance. So think VQE for a single molecule, think QA for a single graph or a single QBO. PCE is polycorrelation encoding, is also a way of solving optimization problems using fewer qubits. QNNs, quantum neural networks, which take data as well as the labels and then do your standard machine learning workflow. Time evolution, and finally custom VQA if you're coming from P&L simplicity, you can pass your object to this class. But this is basically what a quantum program is. It's something that basically solves one problem, one instance only. And one step above that is the ensemble, which I have mentioned before. And this is basically an ensemble of programs, so multiple instances of this sharing one backend. And in Divi, we currently have 3 concrete implementations of this. So we have the partitioning program ensemble. This can take a graph or a QBO and then break it down into smaller instances automatically. So you don't need to implement the partitioning logic yourself. You just need to configure basically how you expect those partitions to look like. And you also have the VQE hyperparameter sweep. So if you would like to do some sort of a sweep across several configurations of a molecule, so say the same molecule but with different bond lengths and so on, this class would also help you simply declare how you want to sweep through this molecule configuration, and finally you call sorry. So yeah, as you said, you just call ensemble.run, and all the generation of the different quantum programs, all the circuits associated with each program would be automatically generated, automatically batched, and automatically sent to the backend for execution. Not only this, but also the post-processing of the results, but I'm getting to this right now with this concept of a circuit pipeline. So each quantum program has a circuit pipeline underneath it. This is basically the low-level manipulation of your circuits and of your problem that gets you all the way from the initial spec, which in this case could be a molecule, could be a QBO, could be a graph, what have you, all the way to the pre-processing of the initial circuit, and then taking it through many of the optimizations or the post-processing steps that you might need for your quantum execution. One example of this is error mitigation, where you need to say for zero noise extrapolation, you need to fold multiple copies of the circuit to mitigate the noise until you finally get to the measurement step and then get the results back. So if you are, say, a high-level user, like one who is has like a standard problem and just wants to use the higher-level classes, you would be interacting either with an ensemble or a program. But if you would like to take things more into your hands and customize the execution how you like it, then you would be interacting more with the pipeline. So going from top to bottom here, you have the more complex to the least complex, but again, the simplest control to the most complex control over the quantum execution. And to give this a bit of like a visual illustration, I did say that you first declare your problem, and as you have seen in the example, this would be something as simple as a hydrogen molecule configuration. And once you call run, this molecule splits into or goes through this spec step in Divi, and this gets expanded into circuits. These circuits then get collected and sent to the execution. And finally, once you get the results, you do a reduction step, which if you're using an optimizer, would then take this result back and basically repeat the whole iteration until your optimization is over. If you're using an ensemble, in this case, you would end up with multiple specs. So if we are talking about the quantum chemistry application, you would have all the different variations of the molecule that you have defined in the sweep. Each of those specs would be converted into or mapped into circuits. And again, these will be batched and sent to the execution. You have the results, and you do the optimization step for each of those specs, basically. And talking more about what exactly happens in the pipeline, so that's the lowest level of our execution, or rather circuit generation routine, is starts by having a spec stage. So this takes your spec, which, as I mentioned, is like a molecule or QOA or a QUBO, and converts it to an internal class that we call metacircuit. And then we do a pre-processing step. This basically prepares your metacircuit for the exact step of the execution that you need. So say think of QA, for example. QA goes through two different kind of routines, all the way from the optimization of the parameters until the measurement of the solutions. So the first is running or optimizing the parameters against the cost Hamiltonian that represents your problem. But at the end, you simply want to measure, sample all the qubits to get the final solutions. And for this, you would need a different preprocessor stage. So one to run against the cost Hamiltonian, and the other to strip away this cost Hamiltonian and simply sample. This way, it keeps all the circuit manipulation steps the same, and even make use of caching, which helps us a lot with performance. And finally, and only like change the kind of step or like step specific changes, manipulations of the circuit that you might need. And the one point to note here is that stages basically fan out the work on the way forward and then collapse the result axes on the way back. An example of this is the quantum error mitigation stage. So I mentioned before, zero noise extrapolation would need to generate copies of the circuit, each copy with the circuit folded chosen number of times. So this, of course, is a multiple of the final count of circuits. But then on the way back, when you did the results, you would then need to apply extrapolation on the expectation values from this QM stage to then extrapolate down to the non-noisy result, hopefully. And so this applies to many things. So also for parameter binding, if you are optimizing, if you're using a population-based optimizer, or maybe doing some sort of a Monte Carlo optimization, you would have the same circuit, but multiple parameters, like a whole population of parameters, say 100 of them. So again, the stage would then fan out one circuit into 100, and then on the way back, collapse them into the one or maybe the multiple parameters that have actually produced the best result for the next step or for the next iteration of the optimizer. And the way that kind of have support for the for objects coming from either Qiskit, Pinelin, or OpenQASM is that we actually rely on Qiskit's internal Rust-based DAC circuits. So this then strips away the Python-specific objects, which can be a little slow sometimes, to a Rust-based object, the one that Qiskit actually uses internally for the transpilation passes. But then we have actually taken this kind of transpilation-oriented object a step up and use it also for the generation of circuits, even before doing any sort of transpilation or compilation optimizations of the circuit before sending them to the execution backend. And so enough theory in a way. Let's jump to more basically live demos. You can copy this, you can scan this QR code now or go to this link if you would like to play along as I demonstrate what I'll be showing. But for this, I'll need to switch the share to the tab. So here we go. All right. So here we are. Let me just minimize this. All right. So let's start with something that we have seen before, which is chemistry in this case. And as you have seen before in the example, we here declare the hydrogen molecule along with the ansatz, number of layers, number of iterations of the optimizer, and we did the result in the end. And so keeping things, and then, for example, we can also include error mitigation here. So here we're folding the circuit 3 times, creating the versions of the circuit each with a different scaling factor. And if we execute basically this program, what you get is a result of the pipeline. I think, oh, sorry, my bad, need to, whoops, okay. Need to switch to a different, all right, here we go. This is the one. All right, so going again. Oops, that's a different problem. So chemistry again, turning on error mitigation and running this. All right. So this basically shows you the pipeline that I've been talking about and the way that it has been sending the circuits to the back end. And so you can see here that the initial spec of that we got from the pipeline starts with 14 circuits. These are the different terms in the Hamiltonian of the hydrogen molecule, the Hamiltonian the dynamics of the hydrogen molecule, followed by a multiplicative factor of 3 for the quantum error mitigation. And then with observable grouping, you then get a reduced number of circuits, because with observable grouping, you can then collect together terms that are commuting. So this way you can save up on execution. And since we're using Kubila, which is not a population-based optimizer, it only needs one set of, it only uses one set of parameters per iteration step. And so we end up with 3 circuits per iteration that we then send to the execution step, which in this case we are simply sending to a local simulation. And you can see here in the terminal output that we had our 15 iterations starting from negative 0.38 all the way to negative 0.89. And this is slightly worse than the ground state energy of hydrogen, because ZNE on non-noisy simulation can kind of like shoot itself in the foot. So if this was a noisy simulation, it would produce good results, but still it's very close to the correct result. So this is for a single instance. If we were to look at how Divi generates different pipelines for multiple instances of a problem, then we can look at a more interesting example here by starting with a graph. Say we start with a graph of 20 qubits, of 20 nodes, which would roughly map to 20 qubits. And say we're trying to solve the match strat problem. And by turning on partition, we end up with this extra configuration object where we can determine the maximum number of nodes we want per cluster or per subproblem. So if we set it to 8, we should be expecting approximately 3 partitions, but it can also be more dependent on the structure of the graph itself. And this is the partitioning program in some class that we have seen before, which takes as input a problem, the quantum routine, which in this case can either be QoA or PCE or iterative QoA. Each have their own pros and cons. QoA is generally cheaper, but requires like a large number of qubits. PCE requires a fewer number of qubits, but requires more classical computation to compute and uncompute the encoding. Iterative QoA takes longer than QoA, but can produce better results because of the way that it optimizes the QoA layers one by one. So keeping it simple, let's go with QoA. Let's go with 2 layers, and let's go with Monte Carlo. And no need for mitigation this time. And also for the interest of time, let's keep it to 5 iterations, and then we call run. So execute this. And here you can see how the graph started and how it was like dissected into the smaller subproblems. And you can then see the different pipelines of each of the subproblems that we got. So we have 8 nodes, 7 nodes, and 5 nodes. If you sum that up, you'd end up with 20. And Then the specs each represent the terms in each Hamiltonian. So we had 8 nodes here, plus sorry, not only for the nodes, it's also for the interactions. So basically the edges of the graphs that you had. So you get the circuits for each, and then all the circuits from each subproblem are then gathered in this batch coordinator, which basically batches the circuits and then sends them to the local backend. And you can see here that we have a total of 90 circuits per iteration. So the circuits get sent, we get the results back. And if you look at the terminal output here, we had those 3 progress bars, one for each subproblem. And finally, we got the best loss and as well as the cut size for the Maxwell problem. So this is for graph partitioning routines. If you look at something else like time evolution, so we can do something very simple, just like running time evolution for a single time step, but then we can check a trajectory, which would then allow us to define a Hamiltonian and then run basically the time evolution for entire sweep of time points for this Hamiltonian. And you can also define the Trotter steps for the time evolution. And one interesting feature that we have in Divi is the ability to approximate time evolution if your Hamiltonian is too dense or too big. So you have the option of evolving your Hamiltonian exactly, but you can also use Q-drift, which basically samples a part of your Hamiltonian and so it does like sampling with the replacement from your Hamiltonian and then only runs that part. And the more you repeat this experiment, the more accurate your results become, the more accurate your approximation becomes. And so if you run this with Q-drift, so let's see, this like that, and then maybe for fertilization steps, and then execute, then we do it again. So we got a pipeline for each time step. This time we don't have any observable grouping because the Hamiltonian, the terms in Hamiltonian are not commuting. And so we have no changes here, but basically we have 10 circuits per term, 10 circuits per program, which in total would be 100 circuits for the run, and then you would get the result back. And since this is like time evolution, you don't have any optimization steps. You just get the final is basically energy of the Hamiltonian. Finally, we also have machine learning. This one is the one with, like, I would say, the most sophisticated configuration, because first you need to specify the number of qubits and then go on with the future map. So in this case, we're using annual embedding, where the value of the future is used to parameterize an RY, a poly RY gate. And then again, we have the ansatz. These were the weights of the quantum neural network would live, a future batch, and labels for your for the machine learning optimization, and then a loss function. And then the rest is very similar to what we have had before. So we have a number of layers, the optimizer, the max iterations, and the master simulator. This would have a very standard pipeline, so there's nothing new to show here. Just wanted to demonstrate the configuration of the Qoro class. So then go back to the slides. Right, and then, all right. So yeah, to kind of sum up what we have seen examples in 4 different domains. We have chemistry, which is represented through the VQE class, and we also have the ensemble version, which lets you try out different, like a whole family of variation of the same molecule. We have optimization, which was represented through QoE, AQoA, and has this kind of bigger brother of the partitioning program ensemble. And finally, like quantum dynamics, time evolution and time evolution trajectory, and finally machine learning through the QN classifier. And although these domains are very different in the way that they are configured and the way that their inputs look like, they basically have the same workflow in Divi. So you declare, then the expansion goes through the pipeline, you execute, and then you reduce all those kind of fragments of results into the final result that you are interested in for your specific domain problem. But then one thing that is very interesting if you're running variational quantum algorithms is the cross landscape. And as it's very known in for anyone who have tried to optimize quantum circuits, that you're very likely to run into the phenomenon of baryon plateaus. And therefore, we have this feature of visualizing actually many things in your quantum program that can help you understand the optimization, or rather understand, debug, or inspect the progress or the trajectory that has been taken by your optimizer through the optimization step. So in the example that you see here, we are doing some sort of a scan and scan through the different parameters of the quantum program, and then applying PCA on the entire history of the optimization and then plotting that. So what you see here is basically the QA cross landscape, and the way that it has been traversed using the two principal components of all of the entire of the entire kind of vector of weights. And you can see it's starting from worst loss all the way to the lower loss, but that's like a very simple, like a very yeah, I would say simple example of what the visualization module can do. It can do many things. So if you would like to do a Fourier analysis of your parameters, you have access to that. If you want to look into the Hessian of your parameters, you can also look into that. Even something as sophisticated as the NAB, if you would like to basically see the bounds of the values of your parameters, you have access to all that in Divi very easily through this kind of Viz module, Viz kind of like a Fluent API. And since LLMs are a big thing now, we thought that we would kind of save you the pain of going through the documentation yourself by building this Divi AI chatbot. So this is a completely local chatbot. You have access to multiple, you can choose from multiple models depending on the specifications of your machine. And once you have the model downloaded, you would immediately have access to the documentation and also the code, specifics of the code of Divi. And you can simply instantiate that by running the divi-ai command in your terminal, which would then spin up the chatbot, and you can ask it questions. For example, this is a user asking, how do I use Divi to find the ground state energy of a helium hydride ion? And the system would then basically walk you through the steps of declaring this program in Divi, and also even show you a sample code that you can copy and immediately run in your Python environment. And of course, this comes with some caveats. I mean, since this is a local model, so it has no access to the internet. If it needs context of other third-party libraries, it only knows it is only an expert in Divi, is what I would like to say. And then, of course, depending on the size of the model, which depends on the amount of RAM that you have, for example, it can hallucinate. But still, we have found that it helps a lot with finding, basically, at least finding the first step towards the application that you're trying to run. And finally, so how good is that really when it comes to doing what it's supposed to be doing? So the first thing I mentioned about Divi is that's meant for generating patches of circuits very efficiently. And when comparing the performance of Divi against the three, let's say, big boys in the open source quantum landscape, tested Penelane and Cirque, we have found that Divi is very, very fast in generating circuit batches for programs that involve observable grouping, quantum error mitigation through ZNE, as well as like twirling. If you're doing polytwirling, again, it's another error mitigation technique, and binding of parameters. So the biggest gain we have seen was for V2E programs. So Qiskit is the kind of nearest competitor, but even for Qiskit, it's like 71 times slower than Divi. For QA, the speed up is a bit more modest, but still, even for Qiskit, it's like 6 times faster than Qiskit. So yeah, it is very fast when generating batches, and this is kind of our PowerPoint, I would say, when it comes to Divi, is that it really focuses a lot on generating batches of circuits and doing this sort of plumbing very, very efficiently, and kind of takes away this, like carries off this responsibility off your back when you only want to focus on your experiment and you don't really want to focus on the scale and or the way that or have you worry about circuit generation, because I mean quantum execution, like running circuits on a QPU, is already slow enough, and so we don't want the generation of the circuits to be a bottleneck that might be hiding in the background and you not being aware of it. And so this takes me towards the end of my presentation. So you can install Divi simply through pip install Qoro Divi. If you want the code to the system, just add AI the square brackets. This is a QR code for the live demo again. If you want a more comprehensive list of tutorials that can take you through a broader range of applications of Divi, all the way from very simple applications to more advanced applications, you can find them on our open source repo. The source, like the link of which is also available through this QR code. And you can also sign up for our cloud platform if you would like to see how it scales up. It helps you like run your experiments at scale very seamlessly. And I would like to announce that we will be having a Divi UX survey very soon. We will be sending a Google form after this webinar, or you can sign up to participate, and we would really appreciate your feedback. But of course, you don't need to wait for that. If you already tried out Divi and found it to be useful, or even found issues with it, then feel free to leave your feedback on the GitHub repo, as well as open the pull request if you would like to contribute. Yeah, with that, I would like to thank you for your attention.
Yeah, thank you. Sorry, I had to turn off my my video because I'm in the countryside and my bandwidth is a little bit low. We have about 20 people on the private audience mode. We have quite a few questions. But maybe I will start with the person on the audience, David. Sorry, everyone, I forgot David. Sorry, I forgot to introduce you. So David is a member of the QF community, a long-standing member, and he will be potentially hosting future open source events. Maybe David, I will open the floor for you to introduce yourself, and if you can ask any questions before I go through the private chat and then go through the public chat,
sure.
LinkedIn, and
Thanks, Bombade.
YouTube.
Maybe the main question I'd like to ask, Ahmed, just to focus on, do you see your primary target user as someone who's not a quantum specialist, shall I say, but rather is intending to use quantum technology in order to address physics or other machine learning type problems? Did I understand that right? That is really who you're aiming at?
Yeah, I hope I got your question right, but basically we want to hide away as much plumbing as possible from the quantum development process so that people can really focus on their domain.
Okay, and then my other main question, and after that I'll hand it over back to Bambode, is in terms of support, if people are wanting to try out the infrastructure, you've got your AI chatbot that obviously is your first line of support, and subsequent to that, if people are stuck, what kind of levels of support do you offer?
So actually, there is a little piece of information that I might have forgot to mention here. So let me quickly share this tab. Um, so if you are using any of the kind of common AI agents, say Claude, Codex, Gemini, whatnot, you can simply point them to this service here. It's called Context 7. It basically indexes open source libraries for you and then provides an MCP server that you can then easily point your agent to, and then you can answer questions. The sense, obviously, this would be like a much larger model than the local model. It should be more comprehensive in its help. And apart from this, we also have a community Slack that people can also join and ask for any like report any problems that they are having if like opening an issue on GitHub does not suffice.
Okay, thank you.
Okay, thank you. So let's see. We have quite a few questions. You are not able to see them because they are on the audience mode only. And I'm not sure because of privacy whether I can state who asked them or pull the questions on the thing. So I'll just read the questions. The first one is, can Divi run different parts of the same workload on different backend configuration, and how is the routing managed? I think they are asking if Divi can partition workloads across, say, simulators, GPUs, QPUs with different configuration. If so, how do you determine the routing for
Mhm.
each specific backend, and how do you combine the results? I'm not sure if
Yeah.
you covered it during the presentation.
So there are several ways to basically control how this process works. So if you do not configure anything, then Maestro will automatically kind of sort of multiplex or route the circuits through the different available backend simulation backends. So depending on the structure and the features of the circuit, we have a regression model that then determines, okay, this circuit should go to state vector, this circuit should go to MPS, this circuit should go to CPU, this circuit should go to GPU. And so this happens if the user does not like explicitly request a specific simulation method. One thing that we have on the roadmap would be to kind of then split the circuits between QPU and simulation. But right now we only have it kind of like focused on only one, so it's either simulation or quantum chip. But yeah, that's basically how it works.
Okay, thank you. We have another question is, how difficult it is for you to add a new backend provider? And a follow-up from the same person is, what are the main limits of parallel execution? Because this is something that you emphasize in your documentation in respect to the current hardware providers.
So adding I'm not sure what they exactly mean by adding a new backend, but if they are talking about adding support from some vendor, then
Yes, yes.
yeah, in this case, if they already have access to this vendor's backends, then they can simply just extract the Chasm circuits from Divi and then send them to the vendor's backend themselves. But us adding like more vendors is, of course, depends on any collaboration or agreements we have with that other vendor. So I hope that answers the first question. As for the second question, could you actually repeat that one again? Just make sure I get all the details correctly.
It's about parallel execution across using the current hardware vendors. What limits you have?
Okay. So
or difficulties?
So from what I know, because again, I work mainly on maintaining Divi, but one thing that we have noticed is that, of course, low utilization. So maybe a quantum chip has, say, 100 plus qubits, but maybe the majority of the circuits that you're sending are 10, 20, 30 qubits. So this is a lot of like wasted queue time. And this is actually a feature that you can have access to when running on the cloud platform is circuit packing. So if you have a lot of smaller circuits, then we can help you increase the utilization of your quantum execution, which in turn would also reduce the amount of credits you need to run a specific quantum experiment by basically like packing all those small circuits into the bigger onto the bigger chip. So this is the one on top of my head, but like I would love to like this kind of user, or sorry, the person asking the question, to ask the question again on our community Slack if they're interested in a deeper discussion on this.
Yeah, thank you. Let's see if we have, that's all from the private audience mode, unless I miss any other question. Let's see on the public channel, which is YouTube and LinkedIn. Guys on YouTube and LinkedIn, do you have any questions before I ask my own questions? You have 10 seconds. Okay, time is relative anyway, so according to Einstein. So I'll give you an extra 5 seconds. Okay, no. Okay, so I'll ask my question. This is more in the context of QF Academy, because we have a lot of aspiring quantum algorithm developers, quantum software engineers. This will be more for you, Ahmed. Is how did you get into quantum software development? And for someone getting started today, what sort of foundations you would recommend them to build up in order to be in a position to get hands-on experience to start their own open source projects?
Mm-hmm. So, I mean, when I finished high school, I was kind of split between going into electrical engineering or physics, and then I ended up going to computer science, so like neither of the two. But my passion for physics didn't really die out. So during Corona, I thought, okay, I mean, I liked physics. I studied computer science, so why not try to merge those two interests through quantum computing? And this is how I ended up kind of like doing some sort of self-learning for quantum computing. And then at the time there was the mentorship program from KOSF, which then connected me with Stephen, actually one of the co-founders of Qoro. So it's like we have been known each other for quite some time, and he was like my first step in building open source quantum software. And from that, I was able to get into an internship at Zapata Computing, and slowly this one thing led to the other. And of course, with each kind of internship, with each kind of like a summer program, I gained more and more experience, and I was able to kind of see how I fit into, like, kind of squeeze myself between all those physicists who are trying to build quantum software. So that's for the first question. As for the second question, I mean, now it's really easier, much easier than before. I mean, at the time, there was no AI agents, there was nothing, not even a chatbot at the time. So now with all the advent of all those LLMs, it's so easy to kind of fill in the gaps in your background using those AI tools, AI models. Especially when it comes when it's still at the early stage of learning the concepts. You can easily tell a model, like, explain like I'm 5, and it will like boil down a very complicated quantum topic to you. And then from there, like, once you have the fundamentals and the foundations of quantum computing in place, I guess the best way to start is to look for, like, attempt to have some contributions in open source software. So Pinelane, Qiskit, and I'm sure CERT as well, and other open source libraries have a whole long list of issues, many of them which can be enhancements to the software or bugs that need to be addressed. And once you find something that interests you, can easily then address that one and open a pull request. Of course, the bigger and the more complex the library, the slower the process would be. So one needs to be a little bit patient and until the pull request gets kind of like merged into the main branch. But of course, people can make use of events like what was it called? Unitary Hack. Yeah, Unitary Hack is where the companies themselves are waiting for contributions, and they need to like merge the pull requests much more quickly to actually disperse the rewards of the hackathon. So this would also be a kind of a very fortuitous time to have transparent contribution and open source library very quickly.
Yeah, thank you. Yeah, I definitely recommend Unitary Foundation initiatives. They also offer micro grants where people can propose. They are doing a great job in trying to foster the open source ecosystem. There's another question that popped up, but I will ask first my question, one of my final questions. I have an extra one, but I'll leave that for the end. In the process of building Divi, what did you wish you knew before you started, in terms of like surprises and these things?
I mean,
if anything comes to mind.
yeah.
I know it's a bit vague question.
No, I mean, there has been this kind of like a persistent pain point when we were building Divi. So as I stressed in the beginning of the presentation, the goal was not to replace what is there, but kind of build on top of it. And unfortunately, like every now and then we would realize that this specific class or this specific module from that specific open source package is not as fast as we hoped, or ended up like hitting a bottleneck at a specific scale. And so we would have to rethink or kind of do our research again and try to find another kind of solution to the specific part of the quantum routine that we want to optimize the performance of. So yeah, I mean, it's always some sort of a hidden kind of trap. You cannot know in advance how fast or slow some open source object or some open source mechanism to work. You have to, kind of stress test it yourself, because you might as well be the first person to use it in that specific manner or that specific way.
Yeah, I guess I follow up of this before I read the question from the audience mode. Is how did, because very often, I won't name a vendor, they make a lot of version changes and these things. Did you get affected in any way recently by a vendor going to a new version, and then they don't have a proper backward compatibility with the thing with what you are doing?
I mean, in the time we were developing Divi, luckily not. So, but I mean, there was one time where we had like a different version locally and a different version in the cloud, and there was like some inconsistencies between the versions. So, but I mean, that's a configuration problem, not exactly specifically the vendor's problem. But yeah, that was very easy to resolve. But no, I mean, as long as you have your dependencies declared like as tightly enough as needed for your library, you should not really be affected much by those deprecations or API changes across versions. I would say it's a very standard software engineering kind of attitude to have, basically.
Absolutely. So here's the question from the audience. He's asking which metrics matter most when evaluating Divi. Is it runtime, cost, throughput, quality, reproducibility, or developer effort? How do you measure success?
I mean, honestly, I would say all of them. I mean, we really want the throughput, like the speed of generating the circuits to be high, but also we want to generate as many circuits as possible without any issues. We want to appeal for both the higher level users and the power users. So we want to make it easy to use the existing classes. We want the existing classes to have intuitive APIs, but also for users who are more kind of like handy, ones who want to build and get ambitious for their custom workflows. We want the internal API, like internal abstractions, to also be consistent and intuitive to them. And part of this is obviously maintaining comprehensive documentation and making sure nothing is like lost in the detail. Anything that a user might need is in the documentation, and as I said again, explained intuitively for them to have no issues. But yeah, I mean, I cannot really point to a specific metric where I measure success, because to us, all of the ones that you have listed are very critical to to like the mission of Divi.
Yeah, thank you. So my final question, unless David has one, is how do you how would you like to see Divi in in terms of the broader open source quantum ecosystem in about 5 years? And also, how can people contribute to the project? I think you already mentioned, you shared the technical link. How is the process for contributing to the project for those who want to help Qoro to get this thing off the ground?
Okay, so the second question is much easier than the first one. So I mean, yeah, it's like the standard GitHub pull request process. We don't really have anything strict so far. I mean, it's not like strict or limiting or anything. Although one thing that really matters.
Do you take AI code?
I mean, if it's good, I mean, I'll review it myself. But if it's slop, I will reject it right away. So yeah, because
that itself can create. Yeah, go ahead. Sorry.
I was saying that when using AI agents in my work, it's always very common that the AI agent would try to like deviate from the abstractions I had in mind. And so it's very common that I just reject what the AI has recommended and steer it again in what the idea I have in mind. Because it always like misses, like always has these like blind spots that it's not able to see. So I think for someone to contribute meaningfully to Divi, they have to actually understand Divi so that when the AI agent is deviating, as I mentioned, they would be able to determine when that happens. As for the first question, I mean, 5 years, I'm not sure if it depends really. Is NIST still going to be around? Is it going to be FTQC or not? But like no matter which kind of domain or era of quantum computing will be there, we think Divi would remain this kind of like SDK that takes quantum circuits from like established quantum packages and streamline the process of like batching and generating, like, rather not generating, but rather yeah, increasing, let's say, the utilization of the quantum backends at the time.
Thank you. Well, I think that's it. We are coming now to an hour, 3 minutes. The time went so fast. Thank you so much, Ahmed. How can people connect with you as a follow-up? I guess you already mentioned the Slack and so on, but I guess you have social platforms as well, LinkedIn and so on.
Yeah, and I think you mentioned me in the LinkedIn post, right? So
yes,
you can all get in touch with me there. There's also the GitHub account. If they stand the page, the GitHub page of Divi, then they can find me in the contributors. Like most of the commits are under my name anyway, so it's going to be very hard to miss my handle. It's Shiro Raven if someone is going through the commits. But yeah.
Yeah. Well, thank you so much, and we look forward to having you back. In fact, I'm talking to your CEO, Dan. Maybe we could organize a hackathon around Divi in the near future. So thank you so much for taking your time for being here. And David, thank you so much for joining as well. And everyone on the audience-only private mode invitation and on the public channels, thank you so much for joining us. And I see you. Have a great day wherever you are. Bye for now.